Okay, this page I think here for the IET network. Yeah. So it's just one of the benefit, some of the benefit for the IET membership. So we do a bit of networking like now, and also if you involved like to be a chartered, raise your profile, and we also give you the libraries access, and we have a TV online. So we also give presentation workshop conferences around the country, and we also assess people for chartership, you know, and which is Chris is a member. So we do give talks and do assess people within Ireland and abroad as well. So we give also mentoring as well. Okay, so this is new. I have to have this because it's part of the legal requirement. So I just give an overview of today's technology. So is people looking for more functionality, more compatibility, so everything compatible to the chip. Nowadays, you see from a system point of view, you have ASICs involved, you have this JESD, which is very high speed involved, and then you have ADC, DAGs. So you can see the complexity of this system. And the things that once you do a design, it's very good for the design, but how you do the testing of it and how you do manufacturability of it. So I'll be talking about these topics as well. So not only just for design, so how to improve your manufacturability, do your testability, look out for bugs, and also I have some areas here that I'll be touching on. So I'll be looking at something about bugs, how you actually avoid bugs, and we look at some of the ADCs, and we look at how MEMS work, we look at some transducers, we also look at the power management of it, and also we look at some of the PCB manufacture, the layout, and the PCB design. So give you the all-round knowledge from a system point of view. So give us a short content. So the best thing I describe, I would be given a short introduction about analog devices, what we do, and we look at some of the sample technologies and what's out there. And then we look at some of the emerging applications. And then we look at what the challenges of engineers is, because the challenges from the design point of view, from a test point of view, even from a technology point of view. And then we look at some of the system design and solution tips and tricks from my archive. So I've brought some PCB that I designed in the past. And this PCB, which I designed some years ago, it's actually about over 20 years ago, was in my closet for a number of years, and I found out even today's technology, this is still very good today. I'll now go through why it's good. And so since this is a PCB I have, I will go through with you what's good about it and why is it still very good today. Even in today's standard, I haven't seen any one design as complex as this or as advanced as this. Even the lamination of this is very special. Not many people even doing this nowadays. So just let you give a background from this design. It's actually for your telephone, your internet, for your video, for your voice over IP, where you Skype, so where you can actually go through 1,500 simultaneous phone call at any one time. At the same time as you're routing your internet traffic through it, your television through it. So actually installed in a lot of those major exchanges like Aircom, BT. Okay. So I'll give you a short description about the testability of this. Okay. So here's a short introduction. There's a few members from analog device probably know, but for major of the people here. So analog devices is in Limerick since '76, and we have in this new building here, and across the way is manufacturing. They do wafer manufacture. So they do a lot of design research, applications, marketing. So this is one of the biggest sites in Europe. It's about 1,400 people. And they have offices in Cork, in London, Scotland, and in Europe and all around the world. So it's very big. It's impressive. When I first joined, I didn't realize the amount of component they do. So they cover a vast majority of the components. So we're having knowledge of the components. You can naturally appreciate then, you know, what coverage they do and how they went through about it. Okay, so here's some of the small sample lists. So we're into aerospace, we're into building, we're into healthcare, we're into MRI, we're in security, we're into white group, we're into military, we're into space, you know, we're into even some of the rovers that go into Mars as well. And we also have chips in CERN where they do the sensing the explosion for the CERN. And they also have those called LIGO that just sense the gravitational wave. They use some of the analog device chips for sensing those gravitational wave. So we acquired Hittite in 2015, and we also acquired Linatech, and we also acquired some cybersecurity business. So give you a broad knowledge that we cover the entire product range and over a lot of applications. Okay, so just to give you a quick sample of technologies and some fundamental of it. So here's, for instance, not people know that we involved into digiports. What does a digiport do is actually you program it, it gives you an analog resistant out. So it's very good for programming. So you program it, it gives you analog resistant out. So we call it digiports. And they're very precise, and you have resistance going through 5K, 10K, and even megohms. Okay. And you have different packages, different resolution, up to 10-bit resolutions. So another thing is MEMS. A lot of people do not know we do MEMS. So MEMS is micro electrical machines. So how they work is actually you have a suspension here on both sides, and then your mass. So and then depending on the acceleration, okay, and it gives a displacement. So you have a spring constant. So the formula goes the spring constant times the displacement give you force. The force is mass by acceleration. So by having doing the transpose of the formula, so you have this constant here, okay, and then by having a constant multiplied displacement, it will give you acceleration. Okay. So how does it work in theory? So here's this one, the silicon inside the chip that suspended and get moved around. So this part is actually a snapshot of these finger beams. So this is the yellow part, which is the proof of mass, and then all these purple one is actually those finger beams, they're sensors. So when you move around the dependent axis, it get picked up by those axes, and it senses the differential of it. So here's how the circuitry works. So you have an oscillator, and then when you get applied the voltage, this beam moves, and then you have two plates. Those two generate opposite polarity. So if the beam's right in the middle, it's the voltage get cancelled out. So it sends no voltage. But if it's moving, it sends a differential. So differential get picked up, amplified, and then synchronized and demotic, and then you get voltage out. So depending on voltage, that's how you relate to the acceleration. Okay. So we look at the next thing is the IMU. So they use a lot of those in the military and the drones for guidance systems. So we have it's an electronic device. So you have three axes that give you coverage acceleration, depending on the X, Y, back and forth, and up and down. And then you have the gyro as well. And then you have three axes of magnetometer. And then you have a barometer, give you altitude. So whenever you get a free axis and free gyro, they call 6 degrees of freedom. Then there's a couple of another free axes of magnetometer, you get 9 degrees. And then with barometer, you get 10 degrees of freedom. So this is an IMU. The compact and very small, about a couple of mils high now. Okay, and people buy them like there's no tomorrow because they're very good in a way that they're compared to competitors, price performance-wise. Okay, so here's one of the questions. Okay, so question one: to integrate a tri-axis accelerometer and tri-axis tilt sensor plus a tri-axis gyro, plus a tri-axis magnetometer, plus a barometer, plus a temperature sensor. Does that give you a 14 degrees of freedom IMU? Okay, the answer is no, because, okay, see, temperature does not consider positioning, okay? So it's not in position, right? And for a tri-axis tilt sensor, it tilts, it doesn't give you a position, it gives you an angle. Unless it's moved with time, then you might able to get something with it. So the answer is no. So it's only down to about, I think it was at the 3, 4, so it's down to about 10 again. Okay, so here's another question. So what's the difference between a gyro and accelerometer immersion angular acceleration? The trick is here, a gyro can be stand still and you move, you still spin, give you acceleration. But whereas the accelerometer depends for the distance out. Linear. Yeah, and then you move it. Because with gyro it can be pivoted and still measuring at the same time. Whereas the further distance it gives this from the center rotation, yeah, it gives a better what you call it away from the center, give you the displacement, you know, the further it is. So one is with distance, one can be stand still. The gyro can be pivoted and then still rotate and give you the sensitivity, whereas the accelerometer has to have distance to give you more sensitivity rotation. Okay, that's where the uniqueness is. Okay, so that's it. Yeah, regardless of the distance. Yeah. Okay. All right. So here's some of the eye-couplers we do. A lot of people is not aware that we do eye-couplers. So basically, what eye-couplers is actually a transformer inside a chip. So there you have a transformer on one side, and then you have transformer on the other side, and then insulated by insulating layer. So these actually been replaced by this optocoupler because due to high power and the size of it. And you see a lot of this being used in the medical field where the equipment has to be isolated from the patient. So, and a lot of people are using this now and replace it with the optocouplers. And this is one of the ICs. So here's the transformers completely isolated, transferred to this IC over on the other side. So it's completely isolated. Okay. And you have a lot of application here. Okay, industry, metering, you know, interface, amplifier. So if you want to, instead of using a bulky transformer, you can use one chip to do the same job.
What about speed?
At speed, yeah, they go into very high. Some of them go up to mega and tens of megahertz now. They're very high speed now. Yeah, so they very high speed. Some of them they keep advancing all the time. Okay, so we look at the challenges, the real world about ADCs. So the real world, my sister is non-technical, you know. When I told her working analog, you know, she said to me, analog isn't everybody gone digital, you know. So we still need analog to do the conversion and digital to do the processing and back again in real life. So you can see it in the sounds and wind scales, temperature, even the smell, and the speed of moving cars. They all need to be related back to the analog world. Yeah. Okay, so we look at some of the ADC technology. We have Sigma Delta SAS ADC pipeline, and at the moment we are breaking the barrier of 3 gigasample per second, something even 3.5, very high speed. And depending what area you're into, like applications, is it in telecoms or in wind scales? So we have something for everybody here. So they are up to about 32-bit precision. So the precision is usually SAS, and the sampling up to about maybe less than 100K. Right? For the high speed here, you have 3G networks. We're working here in the 3 gig sample per second for the 5Gs. I actually work with a few customers in the University of London. They actually do some 5G network for the major players like Microsoft, BT, and so forth. So I've been recommending and working with them for the next generation 5G for their customers. Okay, so look at the ACD specification. it's something we need to know. They always give 3 different type of specification: parts per million of full scale, percent of full scale, dB of full scale. So they all kind of related into a number of bits to give you the resolution and what the resolution granularity you get from those scaling. So just give you an example that when you're done 24-bit, you're down to Johnson noise. Okay. So as you go to 24-bit, the noise is a very important factor that you need to take into account. Okay. Okay. So another thing that the ADCs you will see commonly is they call dynamic non-linearity and the integrated linearity. So what do they all mean? One is actually measuring from end to end, give you the full spectrum, where the other one gives you an average from the top to bottom. Okay. Right. So one of these things they call signal to noise ratio, and if your ADC will give you this resolution. This is a famous formula, give you the gain 6.02 n. N is the number of bits plus 1.76 dB. So I wrote a paper about the derivation of this. When I started in analog, a lot of people wasn't aware where those numbers come from. They were just pulling left, right, and center. But then one day I noticed a lot of people did not understand where those numbers come from. So I spent about 2 hours deriving it from first principles and on a piece of paper, and then I was just for my interest. Eventually, I talked to one of the authors. They said, "No, it's very good." He told me to publish it. I think I'll publish it. So one of the published called MT229 gives you the derivation where all those numbers come from. Okay, and then the quantization noise is called dynamic range. So to do with the process gain, and then you have the spurs. Spurs is actually folding back of those harmonics that you see further down the field. So the noise will be just down here. Those are called spurs. Spurs is actually harmonics that have been replicated, folded back in time due to frequency folding. Okay. Okay. So here's a question. Some of the people who want to do the ADC calculation for their application. So you say, if I require to solve a system with a 0.4 PSI, what kind of ADC resolution I require? So then you go through plugging in formula, the resolution is 0.4 divided 1,000 gives you about 0.04%, which is 1 over 2,500. So you say, well, for a 10-bit will give me this, won't cover that, so you say 12 bits. But then, okay, 12-bit, that'll be a good starting point. But then I have an amplifier in between, so I need the amplifier to give me 2 volts to give me the full dynamic range. So when you work this out, if this ADC is with plus or minus 5 volts, then you plug in this formula, so it gives you 1/5 of the range. So multiply this will give you the number of resolution. So in other words, you need a 14-bit ADC in order to cover this adequately, otherwise you lose information. Okay? So here's some shortcut that rather than do all this calculation, you can use this cheat sheet, they call it. That you pick your application, and then you can more or less can define your resolution here. So if you go to weight and scales, you'll be in the 24-bit range. If you look at the military and radar, you'll be talking about 12-bit and very high speed, you know. Okay, so this gives you an idea. Rather than do all the work, and you can always pitch what application you use to what ADC you can pick up rather than do all this calculation. So it gives a kind of a shortcut. Okay. Okay. So now we look at some of the immersion applications once you understand the technology out there. Okay. So we look at some of those technology out there. So it's very common now. They call it FMC, which is they call Fpga Manzoni card. So it's kind of standard for very high speed. So you have a single width and double width. So if you're not familiar with the JEST, it's actually it's a interface that they had for a couple of years now. So they go through the revision A, B, and C. So I'll give a quick snapshot of it. There's some of the standard, you can actually go to 12 gigabit per second, and at that high throughput. And the C standard can go up to 20 gigabit per second. So it's very, very high. So So you have called high pin count and low pin count. You can mix and match it. The difference with the high pin count, you have 400 pins, the low pin count is 160. So sometimes when you see they're almost identical, but actually the part is different. So if you look at those, one could be high pin count and low pin count. If you use low pin count for the high pin count device, you will lose a connection because they're actually two unique parts, and although they look identical, some of the pin copper is not populated, so it's actually not connected. So be aware of that. So a lot of people fall into that mistake. Okay. So here, the reason for using the JEST is, if you look at, for instance, if you have a 32, 34 wire system into ADC, and then to FPGA, then you're going to look at those wires, number of wires you need to connect. It becomes very complex and very awkward, to route, and as well as that, run out of pins. So they come up with a solution with JEST204B interface. They call it 0 pairs. So actually 1 or 2 pairs can mop up 34 lines. Okay, so you can have the same design, but your number of connections drastically reduce. Okay. So this is some of the newer standard they've been out for quite a while now. So I think about no more than back in 2006, so about 12 years old. So they keep advancing all the time. So I'll give you a snapshot of the A, B, and C, and recently they ratified the C just only last year. So again, it's called, they use the common mode logic. And why it's important, you can go up to 12 gig for the B version, and it's usually point to point, and it's unidirectional, and normally DC coupled, but compared to the LVDS standards, they're a little bit higher power because you have to be biased, ready to go, so they consume a little bit more power. And if you compare to the LVDS, it's actually 4 times as fast, but 4 times as less I/O. And when I work around, it's about 2.5 less equivalent output power if you want to compare one for one like. So one of those common mode logic pair is actually equivalent to 4 of your LVDS pair. Okay, so even though if you compare 1 to 1, it's a bit more high power, but when you compare the 4 of them to have the equivalent throughput, is actually you're saving up almost a factor of 3 times. Yeah. Okay. Okay, so here's some of the quick crash course. Just you have the FPGA or ASIC talk to the converter. So you have one link is 1 lane, so you have multiple lanes. So 1 link is actually a pair of differential pair. So you actually so they actually go unidirectional from one way from the FPGA to the for converter, or the other way around. Okay. So the speed can go from 300 megabit to up to 12 gigs, and you have determinate latency. So you have a device clock, which is common for the 2, and then you have another clock for the other one. So, and then you have just a quick summary where the A, B's differentiate from. So the lane has increased for the B standard up to 12 gig. Then you can do multiple lanes, and you can lane synchronization. You can have deterministic latency, so you have to control your delays at the same time. So if you want more information, you can see this JEST is free upon registration. And then there's some AD have a lot of learning archive there for people who want to know more about it. Okay. Okay, so like I said, the C has just been ratified there last year. Okay. And a lot of people are working on it, so you see us slowly introduce more the C standard now. Okay, so one of this emerging application you see is a lot of people doing energy harvesting from the house, converting the solar energy, and a lot of people are doing a wireless network for homes and industrial. And you see a lot of buzzword going around the Internet of Things and how to control temperature. And there's one company using this IoT to control, they call Internet of Tomatoes. So they controlled farming as well. So they control the tomato, the temperature, the humidity, the sunshine, and they've found that by doing that, the tomato is actually sweeter. Yeah, sweeter. So you have a lot of people doing uniqueness of it, controlling it. Yeah. So we have people using in farms controlling this, the aggregation of farm, the water flow, the drainage. They're using GPS and sensors, gyros. So a lot of people into this as well. Okay, so another thing that analog device also big into automotive. So analog devices came up with this start-stop technology out there in the Mercedes and other cars as well. So that's their technology. So we're also involved with plug-in hybrid electric vehicles, battery management, and also the advanced driving assist and autonomous vehicles. Okay. So here's after all this, we talk about engineer challenge involving time. So what are the challenges with all this technology, or the chips, the design? So how does all work? Okay, we look at for an implementation point of view from a project. Okay, so normally in a project you have a pot of funds. So how do you make most of the funds? Right, you can actually pump in more money, and then you get more time, more equipment, you get more software, you could outsource it. But the thing is that by doing all this, is what's the value at the end of the day? Are you making most of your value? So my take on is that we try to reduce what we can, but there's no shortcuts, but that should help to improve a lot in terms of manufacturability, design, and what we can do by having a lot of the design into your design to test your design and test manufacturability as well. So with all these improvements, actually help to reduce, and but like I said, it's actually for testing purpose. When you do characterization, you need good equipment to characterize it. Okay, so there's no shortcut, but we talk about how to speed things up and improvement. Okay, so in the real world, with the project, you have required equipments and so forth, but in the real world, it doesn't happen from the reality. So it's always much overspend, and you might come to tools, equipment, licenses, and so unforeseeable things down the line. Okay. So and the other things that you could come across bugs, especially when you hit bugs, you'll be talking about months to fix it, and then if it's happened further down the line, you need to restart everything. And the worst thing is that you have recalls, which is not good image, out there if you have so many bugs not being pulled. And I see a lot of people out there with recalls, which doesn't give you a good perception if they have so many recalls. So avoid losing face. You try to do it right first time. Okay, so here's the time scale. So here's the cost, and here's the development time. So I call this milestone. So you design simulation and go through a PCB layout. So you hit those milestones, and if it doesn't work out in production, you try to avoid all costs of recall. Otherwise, the cost escalates dramatically. So we try to say, okay, what improvement we can do? We try and focus more down here. What we can help actually improve without any recall to first time, and help the production at the same time. So avoid redesign, recall. If you're down here, recall, you all go back to the drawing board again, you start again. So you can see the escalation. So I'll be talking about some of the design, simulation, and bugs where we try to catch, and how we can actually improve it from a design and simulation point of view. So I found that in the past that when you do a complex design, it's very good, but then how are you going to test it? Because like a board like this, it's all pins. You hardly connect anything on here. So I'll talk about this board and the testability of this board. Okay. So we look at the challenges. So it's always defined by customer. They want more and more functionality, and as the silicon geometry goes down, you compact more functionality in there again. So here's actually one of the design they call software-defined radio in one of those chips. Very highly complex. It has a filter, digital filter, analog filter. It has modulators. It has ASICs. It has you know, in up and down interpolators. You have VCO. It has PLLs, you know, and it has two transmitters to receive. So complexity goes up, and then how the best to test this, it becomes a nightmare for the engineers and the test guys. So usually you have a functionality and complexity increases and pin-out packages. Okay, and then no matter how good your design is, if it's not testable, you know, it doesn't make that design very good. Okay. So I said good hardware design, but only half the story. So what we want to do is to make a design better, faster, and smarter. Okay. So we look at some of the project timeline, overview, return on investment, how good your design is, and we look at some of the solution and design challenges. Okay. So when you want to do a design first time right, there's a lot of factors to do it. So you want to design for testability. That means minimum equipment interaction. So you could be having very expensive equipment, but then connecting it is a problem. So you try to design for testability at the same time, not just your design. Then you want to design for functionality. So design the test to test your design. Okay, that's another challenge. You know, so no matter how good your design is, okay, but you need to design to test your test design without actually breaking the bank and having expensive equipment. Right, and then you have a design for manufacturability in production tests. Some of the tests you see that it takes about half a day, 1 day to test the design, but actually you can improve the design way, way faster. Some of the design I did is I completely revamped the production design and haven't factored into this design. And normally the test take about 1 day to test the equipment. With the design incorporated, and they can test it and have it out the door less than an hour, within an hour. Okay. So then you have the design for first time right. Okay. And then design to speed up your tests and design to time to market. Okay. And then you have the design for flexibility. Here's another one for flexibility. A lot of design, you might have variants. So you might have 4 or 5 different products having the 4 different 5 PC, but can you actually common them up, have one PCB that can do the 5 products? So you actually, which I've done in the past for another company here in Shannon in the mid-90s. I actually mop up 5 boards into 1 board that help the infantry, and then they can, depending on the board they want, they only need to populate as they go along. So it helped reduce infantry costs. So having that is a big help. And then the last thing is have a design reduce no bugs, no respin, no recall. So if you, and they all interact one way or another, but if you can do all this, I call that this an achievement. Okay. So here's a design for testability. I always find that have your design that you spend some more time here and add in about 15 to 20% of extra circuitry in your design to test your design for testability. Okay. All right. So you add about a little bit more here. So I talked to people. They said that okay, they don't do much here, but then they do a lot here. So it's like balancing out. You either do some more in the front end, or you pay more expensive to do at the later end. So you take your pick. So you have to do one way or another. But I find that it's actually cheaper, faster, and more economical to do it down here, because if you go along the line, it escalates the cost dramatically. Okay. So we'll look at some of the design cases. Right. So we look at some design case, the ADC interface, and model it and how to test it. So I found that even some of the customer support, one customer particularly, they came to me. They said they've been testing that for 3 weeks, and it works normally, but when they crank up the high speed, it does not work. So they've been troubleshooting for 3 weeks running, and they couldn't find the issue, so they came for me for help. So I looked at the design looks okay. So I look at this, the layout, the layout looks good, so I asked them for a timing plot. And with the timing plot, I said to them, look, it's an easy fix for you. that clock, just invert the clock and should be okay. And he looked at me and asked if I have two heads, you know. And I said, we spent 3 weeks at this. And he said, you tell me just invert the clock and it works? I said, yeah, try it, you know. So eventually I persuaded him, he tried it out and it worked, you know, first time. So it shows you, you know, they haven't perfected the interface here and they have issues. So I just give some example design that I've been doing to help to do the testing, the interface, before you even have the PCB. So you test now, you know when it's working, and when the board comes back, you run it and bang, it worked first time right. So these some of the achievements that most engineers should able to achieve rather than go to spend 3 weeks in doing interfaces. So we look at some of the testability as well, how they speed up the manufacturability. And we look at some of those unique tricks. I come up with automatic insertion for connectors and what the benefit is and how why one does it. And we look at some of the bugs. This is bugs. So even though it's ASIC, I found that people have the same problem even when they write window programming. And I'll go through that, some of the bugs that they apply and how they actually reduce it. So it's not only ASIC, but you can propagate all the way up to C code, window programming, hardware. So they all fall in the same category. Okay, so we look at one of the design cases, control interfaces. So one of these, we look at the protocol interface to how you control it through the FPGA or ASIC or even the microcontroller. I use the ASIC because I don't want to use this other people's compiler. So it's easier, faster. I have my own tools. I get it done fast and quicker that way. But people can do the same thing with a microcontroller. Okay. And we look at some of the model, how you synthesize your ADC from a model from a test bench design. Okay, so here's one the design I did for customer, and it's interesting. And so I did a small ASIC. The customer originally came to me and asked for help for ADC. We picked an ADC for him, and then he asked me how to recover it. I told him to get a DAC, and then he said, how do you control it? I said, use either microcontroller or the ASIC. And then when I was talking to him, you know, he's a retired professor, and then the work he's doing is interesting, but what made me got involved with it, I told him, look, I'll voluntary do it for you for free. I'll do it in the weekend and evening, yeah, to get this done. So this is a snapshot of the test I did for myself because I don't have the expensive equipment at home. So my trick was to use the capability. I do this system test, do as much test as possible with actually just using simple oscilloscope. So here's a design. Here's an ADC. So to interface the ADC, I have to model it. So I didn't get any model from anyone, even though I know the ADC. So what I did was I look at the data sheet, I look at the timing. From the extracting the timings, I managed to work out the state machine I need to do to interact with it. So from look at the timing specification on the data sheet, I managed to extract the timing, managed to do some modeling, and actually do some uniqueness in doing 4 different channels, and I modeled the different channels because all I'm interested is interfacing the transaction of it, make sure when the PCB comes back, it works first time right with any bugs. So I start modeling it this way, and then I have some random number generator generating these bits, and then I have 4 channels that denote my 4 channel, and then this number ADCs, 2 ADCs. So I start design my ASIC transaction to model to get the information back and forward, and I have a loop back as well. So the loop back is actually quite unique because it tests the whole functionality later stage for fiber optic applications. So just this interface here, I managed to model. You can see that by spending some time in your initial stage from your design at the project stage, you can do quite a lot and model quite a lot. And then when the PC comes back, you can actually work straight away with actually debugging with it, yeah. So it just shows that it can be done. You don't need to real the ADC number, but you need to just model it in a certain way and grab the information back and forward, and then you check some timing to see will it meet your timing specifications. Okay, and that worked out very well. I think that took me about 2 weeks to do. okay, and in my own spare time, at weekends and some evening work, okay. And when I did the whole system, I managed to publish an IEEE paper from that because it's quite unique. It hasn't been done before because it's actually for sauna applications using fiber optics, and before actually have massive cables laying out, and so for fast deployment and rapid deployment, you can deploy it anywhere in the world within 24 hours without actually having a vessel with a winch and a crew of 30 people, and it take you 2 months to get to your destination. So it's quite unique. Okay, so here's the one that design talk about this board. Okay, so I'll pass it around. So this is they call carrier, and this is called model card. Okay, so just look around. And here's one of those called DSP. It's quite unique, this DSP board. Okay, quite unique. How many layers? 8 layers. So we try to do with 8 layers. We managed to go with 8 layers. Although 12 layers would be good, but then we try to compromise. Can we get away with 8? So we managed to get away with 8 by having uniqueness. And there's about over almost 500 ICs combined the two. So this PCB is 9 DSP on one side and 9 on the other side. This DSP is 1 square inch, and there's 100 pins on those. And the design that time is about the 1.8 volt for the core. So here's 1.8, 2.5, and it's about 3.3. So this board with 18 DSP on it, and they plug into this unit, and you can populate 10 of those, and then 2 on here. So on the DSP alone, you have 200 DSPs, okay? 200 DSPs, digital signal processors, and 100 pins. They're so small. And this was a challenge in even laying this out because you have BGA on both sides of it, okay? And this is a model with ASICs and Fpga on it, memory, RAMs, buffers, and try to JTAG over 200 devices challenge itself. So we try to JTAG 200 ICs, you know. So that was a challenge by its own right. So what's good about this is actually to have a lot of those built-in functionality in it for testability, because I work with I was responsible for designing these boards, and then I work with the ASIC designers, the FPGA designer, how I want it, how I want to architecture. So we talk about this, how people might pick up ideas and learn from it. Okay. Actually, even today's technology, this is very good in today's standard. This board, they use sequential lamination. So what they mean is that the wire do not go through each layer. You don't go to a layer that you specify, and then it laminates, seals off. So it doesn't go all the way down. So it only go per layer basis. So it becomes very expensive. Not many people do it nowadays, and not many people even aware of it. This can be done. Okay. Okay. So what's uniqueness about this board? Okay, here's about testability. So in the board, you have many FPGAs and DSPs. So how we actually design this? Like I said, the design is not a problem. It's just designed for manufacturability. So in case there's shorts on the tracks, and if it doesn't come out right, so how are we going to test to help out the testability of it? So what we do is that I have a system diagnostic test. So you have those loopbacks here. So this FPGA will talk to this guy and have the tracks running across it. So when this one sends the information here, and this loops it back, and if we receive the same information as you get back, and that means that the manufacturability is good. So the track is not shorted. So that's a help. And so what you do is you pump in those tests, pattern tests. So you alternate 5-5 and then AAs. So give you, if there's a short of the track, you will see it connect to the next track. So you see a short, you won't see the same pattern. And then you do some other tests as well, alternate tests. And then for this test, you do, say, loading test. You load it with 0, load the FF, see can the board handle the power, okay? All right, so and then you do a bit walking test and walk your bits over the lines. So with this way, what happened with this is, so you open this loop, so you connect this loop, you send the information back, loop it back, and you know when this is working, then you open a bigger loop. Okay, then you open more loops, and then when you open more loops, and then you open more loops, more loops. So you can see it, you can test your board back and forward, inside out, and to help manufacturers, rather than have a technician there testing each track, what's going on, this actually can actually narrow down exactly, pinpoint what track is shorted. Okay, and that all that testing can be done in less than 5 minutes. It's that fast. Okay, so we'll, is that test? Okay, so we look at the test case 3. So here's another called smart connection test. Why we need it and what's good about it. So if you have a number of connectors, okay, right. So if you have a number of connectors, the last thing is if you want to detect what's plugged in, if it's been plugged in, and does it need to be configured or does it need power. So having a bit of a technique, I call this, I put in some resistor detection here. So when you plug in, it shorts it. So I have this permutation there. If it's no module, you can detect it's 1-1, there's no module plugged in. And if it's module X, you can actually short the 2 depending module, and then it can detect that is module X, and then you can configure it. And then you can put another module there, Y or Z. So you actually, by plugging in, you know, it might need to be power, but you don't want to power when there's nothing there, even though it does not draw current, but the power supply itself have losses, you know, having standby producing the power. So you can actually power down your power supply with actually, you know, reaching that to destination. So once you're plugged in, you can actually start power up your power supply. You actually can configure it. So you can see the different boards, maybe a different DSP, and then different type. So you can actually configure exactly, you know exactly what's on your board, if it's been populated, what's been populated, and does it need power. Okay. So with this way, it's actually more efficient. Right. And here's one of the design that if you have long track, you put in 2 capacitors to reduce your noise. Okay. All right, so look at this cases for eliminating bugs. So I call it a Ching's category of bugs. So I've done quite a lot of ASICs, and I still see people, even software, hardware, and they still have bugs. So I classified them as silly bugs that they usually caught by the debugger. Even normal bugs like within bound test, you test within bound, and incomplete assignment or incomplete statements. Believe it or not, still a lot of people fall into that trap. Okay, so here's one of this case that actually I tried to work with customer. A customer designed the I2C, and what happens that they designed the I2C, they write to it, and then when they read it back, it resets itself, so the register disappears. So every time they read it, and it disappears, you know. So this actually falls in that bug, you know, incomplete assignments, you know. So you still have people fall into that category. And extended bugs, I call it outbound condition, that you want to test your design outside your boundaries and see what happens. So I'll give an example of that. And then you have rare bugs that you only find them 1 in a million. Okay. So we look at the extended bugs. Okay. So imagine you have memory you want to access. You can read and write it, okay, but what happens if you read outside this memory? The whole thing collapses, and in simulation it hangs, you know. You need to kill the process, and in hardware, if you come across some hardware system that it stalls, even you press reset, will not reset it, you need to power up and down in order to reset it. So when you see a situation like this, it's actually it's extended, but they haven't accounted for testability outside the area. One day, one of the colleagues, even in Windows, they have that problem. And the guys, my colleagues' PC will keep crashing, and they keep getting a blue screen. And I walked by, I said, why keep crashing? Don't know, but keep crashing. And I said, let me have a look at it. I said, I see your problem. He's running over hard disk space, and it goes down to about 7-8 meg, and the system crashes because in Windows itself there's a setting there for caching. They cache about 10 gigs of space, yeah? So when it goes down, it looks for memory and it's not there, the whole system crashes. But if the software designer does better, if it goes down to a certain hard disk space and the caching is 10 gigs, they should start have a dynamic routine to reduce the caching, or warn the user that he has low hard disk space for caching, rather than crash out and they have a blue screen. So you see a lot of designer, even Windows, fall into this trap. They have not tested extensively. Okay. So here's here's one of the rare bugs I come across in my ASIC design. It's quite unique in a way that I try to remove bugs, and in this test, there's a lot of combination permutation. So what happens is this test case 1, say a variable is sequential 1 to 1000, and in the middle it ramps up, and then in halfway up 500 in the middle case it start flip the signals and then start ramping down. So this is kind of test. So you can imagine this could be your voltage test that you need to ramp up and down, and then once you ramp up and down, okay, then you go to your variable X, and then variable X will do another parameters, and the same thing, you ramp it up and down, and then halfway we ramp back the other way. So this kind of test, so you can see that when you do a test 1 to 1000, you say sequential 1 to 1000. Once it's done, you stick this to 1000, you go to this variable, and then this one tests 1 to 1000, and that works well. This one's nailed down to 1, and then start testing this one 1 to 1000. So and then go to this variable, okay? And then once you have this test, you start, so you could be going to 500, and then you go test this again. So you can see this like a Monte Carlo analysis testing method, okay? So same thing with test 2 case, then you vary that. So in one of the design, I do this test, and what caught me interest was everything worked, but only in a certain combination when this variable reaches 500. If this 500, this 500, this 500, this 500, this 500, this 500, it does not work. It only happens in that combination scenario. So, and it took me quite a while to find the problem was, so when I look at the code and I start looking deeply in the design, so this is actually boils down to this code. If something happened, do this, else do that. There's nothing wrong with that. But then when I change the code, that's not what they want. When I had to when I change the code, oh, so I go back. Okay, when I change the code to this scenario here, just if something happens and if, so this is actually what I want to synthesize in the hardware. So you wouldn't dream of it, this is actually a bug, okay? So by only going through the permutation combination, thousands of illustrations, then this bug pops up. So when I found this bug, it actually found in good time. Otherwise, the company I work for in Galway had to pay $4 million to respin the ASIC, yeah, and they have to wait for 1 year waiting slot to have that fabricated. And I managed to cut in time with actually going to fabrication. Otherwise, it would cost $4 million a pop, you know. So 4 million, wrong, go back to another 4 million. And as well as that, you waste 1 year time because they give only a certain slot in the year to have that. So they had to wait for a whole year. So luckily this was caught. And luckily, I thought just my code, it actually happened to other people's code as well. So I managed to catch a couple other people's code in their block as well. So this was a good catch. So I find that it's a rare bugs because you can only catch it in by exhaustive testing it using Monte Carlo analysis method. So a lot of people does not do a lot of testing, and then they might have 1 or 2 occasions that they see this bug, and I've seen that happens. Okay. So here's one of these challenges about routing. Okay, so it gives you an idea. So I want the high-speed design. So imagine you have 2 TQFP chips, and then you have BGA here. Okay, So imagine you work on a 4-layer PCB. And let's say the scale is 1:1. This is actually your board. Okay, and here you have your black is your data, red is your address. You have control here, and then you have this the full color dot is actually your IOs. This is your power and ground. So here's one of these things is if you want the FPGA to talk to those two guys, how best to place the phone component in the PCB and how best to route it. Okay. So how we talk about how to best to place it first, okay, and next thing is how we actually place it and route it. Yeah, do you understand the problem? Okay, the problem is that I want to route connection this FPGA to those two guys. Okay, so the things are how best to place it to route it better, so to avoid crossing the wires and long wires and you know, inefficiency. So you want to route it efficient and without crossing it to avoid crosstalks. Okay. So, huh? Top bottom? Yeah, top and bottom. Well, you could do that, yeah, top and bottom, yeah. But we just, but then don't forget you have 4 layers to play with, okay? Then you have one layer is for one layer. We use single supply, so you need 1 layer for power, 1 layer for ground. So you have 2 layers to routing, okay? Right? Okay, so you could place them top and bottom, but then you have problem because this FPGA, when you place top and bottom, the wires still need to cross over back and forth. If you put up the other side, so that's in the middle, you cannot put anything below because those pins propagate right through it. So nothing can go on the middle. So that means you can go. I need to go across it. So if you go across, depending which way it is, then you might have crossing the wires. Okay, that could work, but not efficient enough. I plow through. Okay, so things that put that in the middle and put the other side orientated. Okay, why we need to orientate it? Because you have 2 layers. Okay, 2 for plane. So we orientate it. Oh. Okay, so the top layer you have the FPGA is flexible. You can actually pin match those pins across the way. So you can actually name those pins uniquely to match up. So you route this on the top layer directly across. So it's direct, straight. There's no twisting, and it's more efficient, right? Short, sweet, and across, and on top layer. Okay. So then you need to connect the other side as well. On the other side, so in other words, the outer layer, even though it go down, but you route it across from the top layer. So then you route it from the top layer on this guy, right? So I'll take out the other one for clarity. And the second layer, which is the second pin, you go down to the other side, across and up. So there's no crossing of the wiring, okay, and routing. So make it very efficient, short and sweet. Okay, and then some people argue, say, okay, but some wires are longer than another. That's okay, because if you clock out your data on the rising edge, and then you clock it in on the falling edge, you give you 50% margin. Okay, even though this is a little big, you only talk about maybe less than ½ an inch away, the difference. So with that technique, and by clocking out the data on the rising edge, and on this guy you clock in the data on the falling edge, so you give 50% margin. Okay, right. So this is how you actually make some routing more efficient and use less layers. Okay, so it works for differential pair as well. So it works for parallel interface. It works for differential pair if you have a pair. So you only have a small bit of maybe 1 mil differences. If you want to tidy that 1 mil difference, you have to curve it a different way to just give you that 1 mil extra line, you know. But usually 1 mil is not a big issue. Okay, and to do some of the calculation is the rule of thumb for the track length. You know, we have MT tutorial code 94. So imagine that the rise time is multiplied 0.5 times your speed of your frequency. So with this all, if you have 100 megahertz, So you actually 0.35 nanometer times 2. So anything longer than 7 inches, you can actually consider as a transmission line that you need to terminate it. So when we talk about here, it's only less than a half an inch differences. So you're very efficient, and you don't have so many termination because you don't give time to give a rise reflection. Okay. Okay. So here's more advanced. So this is what the other techniques is doing here. So this is more advanced now. So if you type for space, so if there's 2 FPGAs and you need to connect them up, okay, there's a couple of ways you can do it depending, how efficient you want to do it and how much you spend on it, and what you can get away with it. So if you, for an easy one, you want to maintain the length, you can connect this outer layer to this inner layer to the first layer, so they maintain the same track length. Yeah. So if you connect this guy to this guy on one layer, connect this guy to this another layer, so they all maintain the same distance, but they're on different layers. Okay. So then if you want to, there's another technique, you can twist them around. You have to go straight across and then go down the layer to across. But then, so what's the difference between this technique and this technique? So with this technique, it's tighter space, but you need 10 layers to do it right. Here, you can actually do the same thing, but using 6 layers. So you save yourself 4 layers of PCB. Okay? Yeah. So you get a gist of it. So here we got 1 layer from the outer layer, go straight across, and that means that one is done. So the next one, go to the next layer, go down across the next layer. So you have 1, 2, 3, 4, 5. So 5, 6, layers does the job. Okay, so that's some techniques that you can employ to do it efficient, to reduce your cost, and to have more. There's no noise, or you try to separate the crosstalks. Okay, and so this is actually the DSP, which is this guy. This guy even does it better because he's doing this way, and each layer does not propagate to another layer, so they're sequential laminated. So this is a very expensive technology to do, and we've been doing that. I've been doing that for about. That's done in 1997. Even today's technology, not many people are doing this. So you can see why this technology is still very good in today's standard. Okay. So, okay, yeah. Right. So if you have version 1, you have a layer penalty. Here you use layer saving. So you trade off for space to layers. So here you see occupy a bit more space, tighter space there, but need more layers. Okay. Okay. So another thing that a lot of people are not aware of what they mean by no connect. So and why they don't need connected. So I just tell people that no connect, do not connect it. DNC, do not connect at all. Okay, because they use it for test cases, and sometimes it's these pins are internally connected. Okay, so sometimes when they say no connect, that means it's not internally connected, it's not bonded wire, so you can do what you like. So and then you see a lot of technology now, they have exposed pads. So a lot of people ask me what they do with the exposed pads. So exposed pad is like a heat sink. So it actually helps to thermal relief, and we have a couple of papers on this, how to best to use it. So they connect it, and rather than connecting a big bulk of solder, it's best to connect through the wire, and the wire are connected to each plane to distribute the heat. Okay, right? And all chips are very. Normally they connect to ground, but not always. So I've written an article on it to tell people be aware of it. Don't connect to ground. Something need to be connected more negative, or maybe more positive. But they need to look at the chip, how it's being done and how it's been connected. So do not assume connect all of them to ground. In general, yes, but some of them could be very specific. Okay. Okay. Here's some tips and tricks know-how. Okay, about power supply designs. So if you have a 12 volt and 3.3 supply, if you require 5 volt and 2.5 or 1.8, okay, it's needed in your design. So the question is how best to tap which line and how to regulate it and why. So you have a 12 volt and 3.3 volts. Okay. Now I need 5, 2.5, and 1.8. So which one I should tap off and regulate, right, to make it more efficient? Okay. Anyone?
I assume you're using a switching regulator.
Well, yeah, switching regulator, or yeah, you could use switching regulator. You could have LDOs, yeah, regulators. So the things are there now. You have 12 volt and 3.3 volt. You want to produce a 5, 2.5, and 1.8. So which one regulator I use, and where should I tap off, or which switch regulator I should use? Okay. Okay. The best approach in terms of noise and efficiency. Okay. So we have a 5 volt regulation. So best to tap off the 12 volt light and use a buck boost regulator. Why? Because we don't want to see there's a 7 volt drop where you use a buck boost regulator, which is they call no way call it called switch regulator. It for efficiency, okay, because you have a 7 volt drop. And what you use in 5 volt regulation, the 5 volt logic is kind of more or less immune to noise, because noise is around about 300 millivolts, so it does not impact that severe. Okay, so for the 5 volt, I will use a switch regulator, go down to, even though it's a 7 volt drop, but it's very efficient, it's very little loss. Okay, and don't need to worry about noise, because noise is about even half a volt. For a 5 volt supply, the switching, if the CMOS is 2.5 before it sees anything drastic, yeah? Okay?
So would you be using 2 linear regulators, or are you suggesting using that one?
You can use, for this one, I will use switch regulator to drop down, okay? For this one, because I want efficiency, okay? Right? Now, the next one is, if I want 2.5 or 1.8, I will tap on the 3.3, okay? And use LDO, low dropout, because you want to have low noise, because your 2.5 volt, your threshold level, 300 millivolts will actually help trigger it, okay? So even though you make a small losses here, but maybe 1 volt, yeah, 1 volt or less, you can get away with it. So, or you can tap off this. So I use a linear regulator, because 1.8 volt. So if a CMOS, 0.9 volt to trigger to have logic high or low. So with this one, I use linear regulator. So this is the powerful regulator. But the things that be in mind, this is a rule of thumb. But some of the linear those switch regulators are very low noise. Analog devices have very low noise switch regulator. They call silent switches. Okay, so you pay for premium for those silent switches. But the other things are, do you need it? Can you get away with it? Can you do it more efficiency by using this one? Only if you need it, then yeah, go for a more expensive IC to do the job. Otherwise, you can actually have an efficiency, and cost-wise, you have to get away with it. Okay.
What speed would they be switching at?
Oh, it's switching about 2 meg up to about 5 megs.
Wow.
Yeah, there's something. It depends on the switches. Some of them switches 800 kilohertz. Some of them switching at 2.5 megahertz, and some of them even switch at 5 megs. Yeah. Okay. So we look at how that related to this. Okay, here it is. So use a buck regulator to down to 2.1 volt, and then from there you use a linear to go to 1.3. Then you can use a buck regulator to 3.6, and then you linear to here. So you actually do a hybrid method, I call it. So when it comes down to full design, this is the actual chip to use. Okay, so we actually help you design it, implement it, and what chip to use to make it more efficient. Okay. Right. So this is actually the part you use. Okay. So here's things that when you come to design, like I said, when you come to design, it's all very good in paper. So always follow through to your layout guys and follow him and tell him what to do. So for instance, this board I designed, and I give it to the layout guy to lay it out. I found so many flaws, and I had to teach him, even though he's done layout for 20 years, because this one takes about 20 amps on this supply. So we just look at some of the power issue that you need to follow through and be aware of it. So he was designing layout this board for me. So at the back of the connector that connects to the back plane it takes 20 amps, okay? And this connector is connected to one layer and one track only. And I said to him, no, that won't be sufficient, you know, because you're taking 20 amps here, but he says no room. This is for a type board, there's no room. The space only about maybe a couple of mils away. So I tell him, look, there's no room. Propagate those connectors and those tracks to the 8 layers. I said, oh yeah, he says to me, I never thought of that. So he did that for me. And then the next thing is, because it's so high power, there's fuses and those fuses, it's being fused adequately to avoid pulling the whole thing down. So one of the fuses with the pads. So these are about, the board takes about 2 amps, so about maybe 1 to 1.5 amp drawn full power. So we fuse it for a 3 amp fuse. So what happened was he did the pads, right? He did the pads, the via, 1 via to 1 pad. The pads, the via is only about half an amp. So I told him that these pads, those via would blow before the fuse would blow, okay? So he wasn't aware of this situation, so I told him at least put about 4 vias there so he can handle the current capacity when you go down to the layers, okay? So he did that, okay? So all those connectors as well, so make sure there's enough pins to handle the current capability. So in the design of this, I always said you need to follow through. You need to work with the layout guide. Don't fire and forget, okay? When you fire and forget, come back to the board, nothing will work. You need to follow through it, even for routine layout. So I spent about a whole month with him in actually laying a board, even though he specialized in the layout. And I'm a design engineer, I'm not responsible for layout, but I have to supervise him doing the layout in order to get a first time right. So eventually we lay out this board and put enough hooks in place to avoid those issues. So the board came back with the test. We managed to test it on day 1, worked perfectly. You know, there's no respin, there's no fault, there's no burning of tracks. The power, it can handle the power. So it shows that you know, the complexity of this, we did that within 1 year. So imagine you have to respin that board. You need to go back to the drawing board to redesign it and the testing of it. Then you have to go back to the fabricate the IC again, and then the board and populate again. You'll be taught another year. So we actually managed to cut the whole year out of the schedule. So it was worked first time right. And in production, they tested, we fly through it. And one of the things I also designed was the Fpga. In the old design, it takes about 20 minutes to configure the Fpgas. So I chucked the whole thing out and I restart everything, designed from scratch. And then the there's about 4 or 5 FPGA, they're very big FPGAs. And then I configure it in less than a second, they're all configured. So rather than for 20 minutes waiting for configured, and this one, bang, 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 5 of them configured in less than a second. So that kind of technology and that kind of technique can help to speed up the test. So imagine you want to test things, you have to wait 20 minutes to configure and then do your test, but you can configure it in less than a second and then run your test straight away. Okay? Right. So we know about IonQ modulation, okay? So the formula, we all seen this before, and this is a circle, the polar plot. So the question is, this is a formula for the E to J omega t, and where the X is omega t, is built in the frequency and time. So the question is that you have this plot going around, and the question is, where's time t on the axis here? The time is actually right in the center, okay? Now the next thing is, where's the frequency? Okay, I'll show you, right? You see this thing going around, yeah? Okay. So watch when I start rotating that. Okay, then you see a better picture. Okay, you see that, right? Oh. Yeah, so see that? See, this is time going through it, and this is spiral. Okay, so you see this is time. Now, how do we see the frequency? I'm going to look at different angle. Okay, then you see the different frequency. So that's where you see the sine and cos come in play. Now, if I see the imaginary part, if I get that right, so more or less that. So this is imaginary part. And when you look at different plane, you see this sine wave, okay? Then we rotate a different part. So look at a different angle. The real part. Oh. The real part where it goes flick that way. Yeah, you see a cosine, yeah? Oh. You see a cosine? Yeah. So by looking this at different angle, you can actually see the spiral come from. It's actually sine and cosine interaction. Yeah. So you can imagine if a cyclist cycling through a pipe, and then you have another cycle with a link-on wheel or going at right angle to him, and he cycled that way, and the wheel goes through a 360, and the other guy spin him around, so he actually go through the pipe and spin at the same time. Okay, so this kind of scenario. So this is quite unique because it helps to people understand where the real and imaginary come from, how to picture it, and actually how to solve problem. Because a lot of people didn't understand where the sine and cosine relate to this corkscrew. So it's looking at different angles. Okay. So here's a conclusion. So like I said, there's many solutions to a problem. How best you tackle it is one thing, and to do it more efficiently. So like you have the two engineers can do the same design, but who can do it better than another by looking at all those scenarios, having those hooks in place, and avoided bugs. So you have two engineers, exactly competent, but actually one does, I call it more passion, have a passion in doing it, rather than just doing it for sake of doing it and do the daily job. So he go a bit more into the design, more thinking of it, and further down the line to do the, have a more passion in it. So that what makes one engineer better than another. So this is some of the tips and tricks come from theory, from practices, and from being in the field. So these things, some of the things I learned as I help to disseminate some of the information, help to people pick up those tips and tricks. So you can see that it's evolving all the time and it's changing well, so you need to keep up. So forever moving pace. So you always need to use some tips and tricks and some insights, and always on the learning all the time. Okay. So the bottom line is the way I see it is solving problems, how to do things better, smarter, and faster. Okay. So, thank you. Thank you.